In the previous video, we looked at solving a second-order differential equation that represented a spring mass damper system. And here, we're going to look at that same problem, but look at solving it a different way. Okay, that's maybe a more general way that can be applied more generally to to systems with more degrees of freedom. Okay, so our original equation was m delta x double dot plus c delta x dot plus k delta x equals 0. And this time we're going to take a slightly different approach. We're going to define something, a delta v that is our velocity. Okay, so we're going to add a new term here called velocity. That means that delta x double dot is equal to delta v dot, and delta x dot is equal to delta v. Okay, so I can rewrite this equation now as m times delta v dot plus c times delta v plus k times delta x equals 0. And then in order for that to really be true, I have to add an equation that says that delta x dot is equal to delta v. Okay, so this is my new set of equations, and actually you notice that this is now a system of equations that has to be solved simultaneously. So we used to have a single second order equation. Okay, so this was a second order equation, and now I've rewritten this as two first order differential equations. Okay, so this contains all of the same information, but I've divided it into two equations that are each first order, and instead of having a single second order equation. And now I can rewrite this as I'm just going to rearrange it as so it looks like this. So we're going to have things multiplied by delta v dot and delta x dot, and that's equal to some things that are multiplied by delta v and delta x. Okay, so all of my derivatives with respect to time I have on the left hand side, and then the delta v and the delta x I just got on the right hand side. Okay, so so notice that this vector over here is just the derivative with respect to time of what I have in this vector right here. And so in general, this represents a more general problem that can be written like this, where we have some matrix B multiplied by some vector, or the change in that vector with respect to time is equal to some matrix A multiplied by that vector X. Okay, and actually this is just as a system of equations of first order differential equations. So previously we had an equation that looked like this, where we had a y double dot plus b y dot plus cy equals 0. Well, that's a second order differential equation. A first order differential equation is just the stuff right in here, and we could rearrange that if we wanted to say b y dot is equal to minus cy, and that's exactly what we have here now in as a system of equations. Okay, so we've got some matrix multiplied by x dot, just like we had something multiplied by y dot here, is equal to some matrix times x, just like we had some constant times y right there. Okay, so this has the same form, and it turns out that solutions to this have a form very similar to the form that we talked about in the previous video for solving first and second order differential equations. Okay, so the form of solutions here we know is that x, the solution to this, has to be equal to a function that has this form here. So we're going to have a constant multiplied by some vector Okay, that constant out front is arbitrary, but we're going to have some vector multiplied by an exponential e to the lambda t. Okay, so we know that solutions to this general equation have this form. Okay, and so we need not only that, but we need the first derivative of x. So if we look at the first derivative of this, it's an exponential function. And so what we get is lambda times c times that same chi vector e to the lambda t. Okay, so chi is a vector of constants. C is just a constant out front. Lambda is another constant, and t stands for time. And so we have our two exponential functions. So we can now plug these in directly. So we're going to take these guys and plug them into our general equation. And what we get out of that is we're going to get b times lambda c times chi e to the lambda t is equal to a times c times chi e to the lambda t. Okay, and so we've got e to the lambda t on both sides, so that can cancel out. We've got a c on both sides. And if we move everything to the left-hand side, and we've got a chi multiplied by each of these, then we can rewrite this as a minus lambda b all multiplied by chi is equal to 0. Okay, so so what we don't know here is we don't know actually two things. So we were given matrices A and B, but we don't know lambda and we don't know chi. Okay, so this is a general eigenproblem, and what we get out of this once we solve this is we're going to get out some eigenvalues, these lambdas, and we're going to get out eigenvectors chi. Now, one obvious simple solution to this, which is called the trivial solution, is if we say that the eigenvectors are 0. So or the eigenvector here is 0. So if we put in a 0 for all of the terms in here, then of course this equation is satisfied. But that's the trivial solution. What we want is the non-trivial solution. So we want the solution where those eigenvectors are non-zero. And so you can show that the only non-trivial solutions exist when the determinant, so the non-trivial solutions can be found when the determinant of this a minus lambda b equals 0. Okay, so we can solve for that first. So we can solve for the eigenvalues lambda such that the determinant will of those matrices there will be equal to 0. Okay, so let's work through this. Let's solve for that determinant using the this original equation that we started with up here. Okay, so so our matrices are right here. So so if we take A minus lambda B, so this is our A matrix here, this is our B matrix. So we're going to do A minus lambda times B. Okay, and I'm just going to put those together here. So we're looking for A minus lambda B. If I take the determinant of that, what I'm going to get is minus C minus MK right there, and then a minus K right there, and then a 1 and a minus lambda right there. So if I take the determinant of that, what I get is M lambda squared plus C lambda plus K equals 0. Okay, so I've actually ended up with the identical equation. This is called the characteristic equation. So I've ended up with the identical equation that I did in the previous video when we solved this using a different method. But this characteristic equation is the same. And so I can actually solve for the eigenvalues at this time just using the quadratic formula. And those eigenvalues will be minus c plus minus square root of c squared minus 4mk over 2m. Okay, so these are the eigenvalues. These are the same eigenvalues, and of course we're going to get 1, 2. We're going to get 2 eigenvalues out of this. And these are the eigenvalues of this exact system, and we're looking at the exact same system as we were before. We just found a different way to come up with these eigenvalues. Now, the benefit of taking the approach that we've taken here is that we can now extend this to systems of equations that are much larger than this. So we're just looking at 2 equations here, and so we got out 2 eigenvalues, but we can now take this to systems of equations that have a lot more equations in them. Okay, so in general, what's going to happen is that we're going to get out a pair of eigenvalues for each degree of freedom. Now, this original equation, we only had 1 degree of freedom. It can move in the x direction, right or left. So that's just 1 degree of freedom. And we ended up getting 2 eigenvalues out of that after either way we solved it, but this way we solved it. We took that second order equation, we changed it into 2 first order differential equations, and solved for 2 eigenvalues down here, okay? Now, once we've solved for eigenvalues, we can actually plug them back into this equation here and solve for eigenvectors that make this equation true, okay? So for each eigenvalue that we get out, we're going to get out a unique or a different eigenvector. Now, it turns out that the eigenvectors are not exactly unique because for any eigenvalue that I plug in here, I can multiply this entire system by a constant out front, and I can still get 0. So that means that constant out front could be swallowed up in this eigenvector here. And so the eigenvectors are unique within a constant, okay? So meaning that you could multiply that by some constant and still satisfy this equation. And so what we need to do is what the eigenvector has is it's a vector of scalars inside of there that have relative magnitudes to each other that matter. So the actual magnitude of each of those doesn't matter, but the relative magnitude of the components to each other does matter, okay? And the relative components of within that vector actually tell us about what's happening on the dynamic within the dynamics of the system itself. It actually tells us the amplitude and phase of each of the components within this dynamic system relative to the other components in the system. And we'll discuss that in more detail when we start to look at the dynamics of aircraft. There's a lot that we can learn from the information in this eigenvector. But because they're not strictly unique, because they're actually only unique to within a constant, the way we usually write these eigenvectors out is we normalize them so that the length of this vector is equal to 1, and then we multiply it by a constant so that the largest component within that vector is real, okay? Because we're going to talk about these, often we'll get out eigenvectors that are imaginary. If lambda is imaginary, if the eigenvalues are imaginary or complex, then the eigenvectors, the associated eigenvectors with that lambda are also going to be complex. And so we will multiply by some complex number in order to get the largest component inside of that to be a real number, okay? And then we're also going to normalize it so that the length of that vector is 1. Anyway, so that's one thing we're going to look at with eigenvectors. Now, where the eigenvectors tell us the amplitude and phase of this motion, the eigenvalues actually tell us the frequency and the damping of this motion. And again, we'll get into this in more detail once we actually apply it to our full system of equations that we have now for this aircraft. We're going to learn a lot from the eigenvalues about the frequency and the damping, and we're going to learn a lot from the eigenvectors about the amplitude and phase shift of that motion. Okay, so one last thing here that we need to talk about is that actually solving these problems is very challenging. So we've done it analytically here, but that's because we just started with a very simple equation. So this was just a single second order equation. In general, for the aircraft, we're going to have 6 second order equations, or 6 degrees of freedom. We just had a single degree of freedom here. We're going to have 6 degrees of freedom on this aircraft because we have translation for each of our along each of our axes and rotation about each of our axes. So that gives us 6 degrees of freedom. So what we have is, instead of 6 second order equations, we actually have rewritten ours as 12 first order differential equations. Okay, so again, this represents 6 degrees of freedom, but we actually have 12 equations that we're going to be looking at solving. And so, solving or going through this process here to find the determinant of these matrices of a 12 by 12 or a 6 by 6, and we're going to be looking at a couple different examples here. That's not something that is simply done analytically. So, we were able to do this one analytically simply because we just had a 2 by 2 matrix here to solve. But in general, you have to solve this numerically. And so I would recommend using something like MATLAB or Python. There are also some Fortran and C++ libraries out there that you can use to solve for the eigenvalues and eigenvectors of a system. And so basically what we'll be plugging in are these 2 matrices, A and B, and then that algorithm will then solve numerically for the eigenvalues and also the eigenvectors of that system. And then we'll use those results to learn something about the dynamics of the aircraft.